Hi everybody, this is just going to be a brief review lesson from our first week of classes. So I'm just going to go over the opening ideas that we covered this first week and some of those ideas, and try to make sure we have a record of them for you to use later on in your studying. So this week we covered our review section of the course, and we first started talking about how the universe is made of matter and energy. So matter and energy. Matter is anything that has mass. One way to think about this in terms of thinking about matter is that matter is something that has a position and it has a configuration, whereas energy is things that have no mass. So we typically think about in chemistry atoms being the smallest unit of mass, and that's probably where we should stop. If you want to talk about atomic physics, then we'd have subatomic particles and we'd have other mass carrying particles. But in our case, we really only care about atoms, and energy is of course carried by its own particle, and those particles we call photons. So I will talk about photons a little later. These are units that carry kinetic energy with them. Okay, I'm going to skip ahead. One of the concepts of the universe is that our universe is hot, so there is always a little bit of energy, and even in the background of space, there's enough energy to have photons at least flying around, and even some subatomic particles. One of the most important concepts I want to really nail forward is the idea of the electrostatic force, or the Coulomb force. This is the essentially driving force for most reactions in chemistry. This is the idea that positive charges are attracted to each other. So two positives would be attracted to each other. So if these were two positive ions or whatever, they would be, similar charges, like charges, repel, and unlike charges, so a positive and a negative, are attracted. And this also affects negative charges, so two negatives will also repel each other. They try to pull away from each other. The electromagnetic force, or electrostatic interaction, is essentially the force, and it is proportional to the magnitude of those two charges divided by their distance, r squared. So in the case of, say, a sodium molecule and a chlorine atom, so there's two ions, the force of attraction between them, so thinking about the force of attraction, we can just take one atom and put the force as trying to reach the center of this other atom. I guess maybe we should reach the side. So the force of attraction to this chlorine atom, this is based on the distance between them. So the distance between the centers here. So this is the distance r, and then the magnitude of the charges. And so in this case, the magnitude of the charges is 1 and 1. So plus 1 and minus 1. And so in this case, the force here would be proportional to this distance. We'll call this sodium chlorine, and it'll be proportional to plus 1 times minus 1 divided by the distance between a sodium and a chlorine squared. And we could do this for any other molecule. I'm just going to do one more example, which would be like a magnesium 2+ ion and a chlorine minus ion. And now the distance is going to be a little bit different, because you now have a distance is relative to magnesium chloride, and each element on the periodic table is a different size. So the force here is going to be 2 now, because it's plus 2, times minus 1 divided by the radius of magnesium chloride, or the spacing squared. Okay, so get that. I think there's a buzz in the background. And so these differences are important, and we'll play around with this a little bit later when we start talking about how big things are and why different salts might have different powers. Okay, you definitely need to know these subatomic particles. I like to use the P plus symbol for protons. I like to use E minus for electrons and N0 or N0 for neutrons. So if I ever write any of those, that's what I'm talking about. Photons, I do sometimes use the symbol H nu. This is for the energy of a photon is based on Planck's constant times the frequency. We'll talk about that in our next unit lesson. So we think about every atom is essentially these components, and in a previous course you may have even drawn out some Bohr diagrams. So if we drew the Bohr diagram, let's just start with deuterium or something, which is one proton, maybe one neutron. So this is still hydrogen. This is a hydrogen atom. It's a hydrogen with a molecular weight, or with an atomic weight of 2. So let me think about that. I'm going to put that 2 over here. And so this is hydrogen 2, and hydrogen 2 would have a single electron floating around. Now, one of the reasons I include the photons in here is because we're very shortly going to be discussing how this, although this setup is true in the ground state, the actual, this part here can, I'm going to shrink my orbital here. Okay, and I'm going to duplicate that, put that over there, take this away. I'm going to erase it. That's what I'll do. Okay. Get that, put that back over here, and I hope you like watching me doodle, because that's what I'm going to be doing a lot. And so when you have a photon come in, a photon of light can hit this this electron, and it can actually cause it to change its position. And so that's one of the things that happens in this in chemistry all the time, especially anything that's sort of got a color to it. I was just discussing how glazes and stuff are caused by this kind of action. So when light comes and hits this electron, it'll pop up into the next orbital, and then it'll release down and release the same photon. And that's how electrons can move around between the orbitals. So photons end up being really, really important. Okay, we discussed some masses of all these objects. There's some interesting physics happening here where the neutron is actually slightly more heavy than a proton, and that's because the neutron has less sort of active energy. The proton is a positive charge. That positive charge gives the proton more kinetic energy, or more of a kinetic nature, and so that comes at the cost of mass. E equals mc squared, so if you want to get energy, you gotta sacrifice some mass for that. That's not something we'd ever test you on. That's more of a physics concept. Both the proton and neutron are in the nucleus. The electron is in orbits around the nucleus, and photons are absorbed and released. We looked up a paper, or I looked up a paper, as I was talking to you guys this week, and I found a source that says that a photon has less than 10 to the negative 48 E. So less than 10 to the negative 48 times the charge of an electron, if it has any charge at all. They can't assume it's 0 because it's not proven yet, and it might never be proven, but it's within error, of course. 10 to the negative 48 is a massively small number. We did a little bit of experimenting. This is a Tesla coil that we did use this week, and this is a beam of electrons here that are flying out from the Tesla coil. Those beams of electrons are traveling up into this cathode ray tube. They are collecting on this plate, and those electrons are collecting so much that they are actually getting ejected. And I wonder if this is real. This is beautiful if it is, but these might actually be the little electron impacts that are occurring here, and the electrons impact all over this thing, and then some of those electrons will actually pass through the little slit in the side here, and we will see a beam fire out. And so that's what happened this week. This beam here, you can see it a little better here, but the beam is right there. This is that yellow beam of electrons. It's traveling along a little piece of metal there that's being colored. And when we applied a magnet to the beam, a picture I didn't keep was that if we use the negative side of the magnet, we could force the beam to go down. And if we use the positive side of the magnet, the beam would move up. And this is how they initially discovered the electron had a negative charge. In fact, they could actually determine the electron's mass by calculating the force of this magnet, how much charge this magnet carries, and then use that charge to push the magnet away. And then use the curvature, the curve that they're getting, and physics, kinematics, and all that to figure out how much mass it has to have in order to be curved at a certain rate. This concept was then carried out into mass spectrometry, and that's how mass spectrometry really works, is we bend the moving of particles, and we use the bend and the amount that they bend to figure out the mass of those particles. We talked a little bit about mass and weight. That certainly discussion would have been a calculation of mass. Weight is is the force of gravity acting on an object. So we are often talking about mass in our classes because mass is a quantity, and certainly chemistry is interested in quantities. To say the word weight, that might be what we find when we use the scale, but that weight on the scale should be proportional to mass, since mass and weight are interconnected through the force of gravity. Now, the interesting thing is that we can determine mass in different ways from just weighing it on a scale, whereas weight can only really be measured using some sort of force measurement. Okay, and then we had a long discussion about potential and kinetic energy, and this is definitely a tricky concept, and we'll come back to this in a few units. We're actually going to finish this unit, and then the next unit will be all about potential energy and kinetic energy. But chemistry really depends on this exchange between the kinetic and the potential. Potential is energy of configuration and position, whereas kinetic energy is the energy of movement. Just going to pop that in here. Energy of movement. So what's interesting is that something like a photon cannot stop moving, so that means that it cannot have potential energy. It can only have energy of movement. Something like a quark and lepton, if those quarks and leptons come close together, they tend to stop moving and they form something that is known as a proton or a neutron, and that causes them to suddenly gain potential energy. They gain mass. And so this is where the E equals mc squared comes from. And certainly lots of other things. So anytime we want to cause something to change its movement, we have to inject kinetic energy. This is how we cause objects to move. So even in the case of the electron that's being bent, we can think of the electron that's being bent by our beam is actually being bent by the magnet. So for a single electron, that magnet, this little bar magnet, is actually sending photons out through the electromagnetic field. These photons are interacting with the electron, and then that causes it to change its direction. Remember, it would have preferred through inertia to keep going this way, but because it absorbs this photon, you have to include that photon into its new kinetic energy, and it changes direction. And that's really how anything happens. Whether it's rubbing your hands together to get warm, where photons are being exchanged between your hands or between the particles in your hands, or microwaving your food. Of course, the microwave has essentially a photon emitter, and those photons are then blown around and heat up the air and the particles in the food, and those photons really they get way down in here, and they cause little water molecules to change what they're doing. And so that's why wet foods like a fresh chicken leg or something will cook very, very fast in a microwave because it has lots of water in it, and those water molecules will start doing something, and that's how a microwave works, is it emits photons that interact with water molecules that were previously in some sort of configuration that was pretty low in energy. They absorb these photons of kinetic energy, start doing something different, a new configuration, new position, and then as they slow down, they re-release those photons as heat. So here's where the heat of a reaction comes into play. We've talked about these a little bit in grade 11, maybe not in a long time. So an exothermic reaction is moving from a configuration with high energy. So we think about this as a high energy configuration to a low energy one. And over here, and that with this difference, the high energy configuration, this is a potential energy diagram. Then the high energy configuration, in this case we have an A and a B molecule, whatever they are, floating around. They become this low energy configuration. So we could think, a high energy configuration might be something like carbon and oxygen, right? And then they become a low energy configuration like CO2. And this is how come CO2 is so hard to get rid of in our environment, because CO2 is a lower configuration than carbon and oxygen separately. Oxygen has a lot of different things it can do, so it's considered a high energy compound. And it also is made of a bond that's very strong, and there's a whole bunch of other things going on. So here we have a low energy configuration, and then a high energy one. And in this case, because you're going from low to high, the amount of heat inputted, the heat has to be inputted. So you can think about this as your cake mix. I'm going to put my cake mix plus your water, your water, your milk, and then they have to be put together, and then you put them in the oven and you get out a cake. You of course do not get your cake, does not come out with flames on them, but you can get what I'm getting at. This one, I don't know what I'm doing there. Okay, so if you want to make a cake, you've got to put heat into it. It is an endothermic reaction. You're reconfiguring the molecules in that cake mix to make a new product that has a higher energy configuration. High energy, we can actually take it in, eat it, and get the energy back out. So can you explain why melting ice is endothermic? Well, when we melt ice, we have to apply heat. So that heat is going in, and that's converting the ice from the low energy configuration of ice to the higher energy configuration of water. What is an example of an exothermic reaction? We have the freezing of water as an exothermic reaction. So the freezing of water, or we could talk about heat packs. And we had a heat pack in class this week where you have a configuration that the molecules are in some sort of high energy configuration. So in an ice pack, It's usually some sort of chloride salt or some sort of salt, and the salt is dissolved. So here's our dissolved salts, and the molecules are separated, and then as you disturb it, the atoms become closer and closer together. The strength of the interaction goes up because of Coulomb's law. Now they're really strong bonds because they're really close together. So that strong Coulomb law attraction is going to resist movement, and if the resistance of movement means the lack of kinetic energy. And so the resistance of movement, no kinetic energy, so that kinetic energy has to go somewhere, and it becomes released energy. And that's why the delta H that is considered as heat out. And then I have some discussion about phases a little bit. I think I'm going to just skip over that. I do really like, if this is solid, the idea that if you have the same phase of matter, or if you have the same type of matter, for example, water, and you think about it in the solid, liquid, and gas stage, then what we're comparing is the amount of kinetic energy. As you heat up the molecule and it changes phases, you can think that the kinetic energy is going up. Compare this to 3 different chemicals at the same temperature in different phases. So solid iron, liquid gasoline, and gaseous helium. If they are all at the same temperature, then the kinetic energy is the same. Kinetic energy is the same. Kinetic energy and temperature go hand in hand. They can't be separated easily. And instead, what we have is something called intermolecular forces. Intermolecular forces. And we think about those as going up. This is the highest intermolecular force, and this is no intermolecular force. And so that's what we concluded with last week is we said, same chemical, different phases. The kinetic energy will go from low to medium to high as you heat it up, but the intermolecular forces are actually the same in all cases because it's the same chemical. Intermolecular forces are part of the chemical's nature. Different chemicals in different phases at the same temperature can be thought of as having the same kinetic energy because the same temperature, but the intermolecular forces are decreased or are different because we can think about, and maybe this is something I didn't mention well enough in class, but intermolecular forces are a characteristic of the chemical nature. Okay, I'm gonna wait a sec to talk about this. Maybe at the end of next week, I'll make another video about lesson 1, and or whenever we finish lesson 1. Okay, hope this helps you out for reviewing at least, and we'll talk to you when we talk to you.